The last time we talked about the second fundamental theorem of calculus, I pointed out the fact that we have to be careful at times when the integral that we're looking at has a function as one of its upper limits instead of just x. We take for granted many times when we see just an x up there and think that's how it always is. But as you notice, even in the example that you can still see on your screen here, we have to take it into account when it's not just x and that it can show up. Now, if you remember when we did the derivative of the chain rule, what you would do is the derivative of the whole function times the derivative of the inside. And so we have to keep that in mind as we're doing this now, because we're still doing the derivative of a function, right? But it's a derivative of the integral. And so we recognize that the second fundamental theorem of calculus tells me that when I take the derivative of the integral, in essence, what happens is they kind of cancel each other out. And I can simply just say, oh, it's e, and then we would have to the x squared. I do want to make a note that that's simply because that's a constant on the bottom there. And so when we do the derivative of a constant, it does go to 0. So when we're looking at this e to the x squared, that's easy. That's no problem. But what happens when this has a function up there instead of just x? It's not as simple as just saying x squared, okay? Because we're not just plugging in x here. In fact, this would be the cosine, right? This would actually be the cosine of x. But before I just tell you what the rule is, let's just do it the long way, just so that we can see it. So we understand that the integral of t squared, so I'm going to write it like this, the integral of t squared would be 1/3 t cubed, and we would evaluate that from 2 to the cosine of x. Okay, and so I'm going to do the derivative eventually, but I'm just going to kind of carry it along with me as we do this. So I have 1/3, and that would mean the cosine of x cubed minus 2 cubed, or 8. And now I do the derivative of that. And when I do the derivative, that 3 would drop down, right, times that 1/3, giving me just 1, and it would be cosine squared x times, right, the derivative of cosine. See, we would take care of that power. That's where that would drop down. But we'd also have to do the derivative of cosine. And you can see there's that chain rule coming back ahead, full stream. So and of course, the derivative of -8 is 0. Does that make sense? So what we want to see here is that when you do the chain rule using the fundamental theorem of calculus, so the derivative of the integral, right, we understand that what's going to happen is that that function here at the top, that upper limit, is going to go in place of that t. So it's the f of g of x. But we can't forget to do the derivative of whatever that function is. So let's just do a couple more examples here. I'm just going to write them up. Let's just say we had, I don't know, t squared minus t plus 2 dt. And let's have this going from 5 to x to the 4th. Okay? So what we're going to do, and I want the derivative of that, by the way. And so what we're going to do, again, remember, you are going to start by recognizing that the derivative of the integral, they're going to, in essence, but what's going to happen is we'll have x to the 4th every place that you see the t, right? But all of this will be multiplied times 4x cubed. And so just to simplify this a little bit better, I'd have that 4x cubed out in front. That would be x to the 8th, right, because you multiply the exponents, minus x to the 4th plus 2. And certainly the choices that could be presented might have 4x cubed multiplied through, but that's sufficient. Okay? So hopefully that at least gives you another little insight. Let's try one more. Let's say we did the integral of the natural log of t. And we had this go from, I don't know, 4 to e to the x squared. All right, and we're going to do the derivative of that. So here we go. Oh, sorry, dt, forgot that. That'd be bad. All right, let's do that up. So the derivative of this, again, we would have natural log of e to the x squared. That would be there. But we would have to multiply that whole thing times the derivative of the upper limit. And so we know the derivative of e to the x is e to the x, but we'd have to do the derivative of that, so that leaving me with 2x e to the x squared times all of that. Now, the question, of course, can we simplify that? I hope you understand that ln and e would cancel each other out, so we would actually have it a little bit nicer. And so this could be rewritten as 2x cubed e to the x squared. And there you go. And hopefully those two examples illustrate my point a little bit more. And of course, you have that within your packets.